Hey guys, I'm Jared Reeser, and I'm making this slideshow presentation to describe my model of working memory. It introduces a very specific pattern of brain activity that I think plays an important role in thought and consciousness. It's not hard to grasp actually, but it's been completely overlooked by modern psychology and neuroscience. In this lecture, I'm going to try to convince you that this pattern should be interrogated rigorously, and also that it can be used to develop artificial general intelligence. I'll present several unique diagrams that illustrate the pattern. I see it as the shape of working memory, attention, intelligence, and consciousness. Part of unraveling the mystery of consciousness is determining the structure of the thinking process, and this model introduces a completely different way to conceptualize that. The nice thing is that this psychological pattern maps onto a corresponding neurological pattern. Together, I see them as forming a unifying theory of psychology and brain science. I know that's a strong statement, but I invite you to decide for yourself. If you're watching this video, I'm going to assume that you have first-hand knowledge of what it feels like to be conscious and to have personal, subjective experiences. That makes you an expert. So please, you be the judge. Again, my name is Jared Reeser. I began developing this model at USC starting around 2003. I've been elaborating on it and gathering evidence for it for 20 years. To find out more about my work, you can visit jared-research.com. Let's start with an introduction. This model offers explanations for the brain basis of consciousness, how the stream of thought progresses through time, how unconscious processes construct conscious ones, how the brain works in a deterministic sense, and how to implement this in a computer as an AI. This work elaborates on these issues while assimilating current theoretical approaches and remaining consistent with prevailing knowledge. Some of the slides in this presentation contain captions that are not necessary to read. You can pause the video to read this text if you'd like to get more detail. However, if you'd rather watch the video uninterrupted, then you can just ignore that text altogether. This slideshow presents a lot of scientific information, but is suitable for a lay audience. Some slides become dense and technical, but please don't tune out because usually the very next slide will be relatable. If you'd like to see the pertinent citations or find more rigorous coverage, I published an article in 2016 about it with the journal Physiology and Behavior under this title, Incremental Change in the Set of Coactive Cortical Assemblies Enables Mental Continuity. Here's the abstract. I presented this model at conferences, written about it in a book, and wrote a follow-up article in 2023 about it, which can be found under this title in the Cornell Physics Archive. A Cognitive Architecture for Machine Consciousness and Artificial Superintelligence, Updating Working Memory Iteratively. I'll actually introduce several different terms, and I'm going to explain them and build on them throughout this talk. That third term there, ICSSC, is the pattern that I was discussing earlier. There's also an entire website dedicated to the most current version of the model at aithought.com. There you can find many more figures and explanations. Here are some of the figures, with captions included. I try to relate the model to as many concepts from brain science as I can, and then show how such a model could be instantiated within a computer to get the mammalian thinking process inside a machine in an effort to provide the architecture for artificial superintelligence, as well as offer an explanation for how an AI's attentional window could be expanded to increase its capabilities. Again, it's aithought.com. Okay, so before I start, I'm going to try to explain the model in just a couple of minutes so that you have a general idea of what I'm talking about and where I'm going. So imagine if we could take the state that your brain will be in right now, freeze it in time, and analyze it. In that instant, there'd be a set of concepts that you were thinking about. And in that same instant, the brain areas that encode those concepts would also be active. Let's say we took a sample of those active neurons and labeled them here 1 through 7. Those brain cells would be in a state of heightened activity, and generally this lasts for a few seconds at a time. But once we unfreeze this system, that specific distribution of coactivity across your brain would not stay fixed. Let's say that after 2 full seconds, neurons 1, 2, and 3 became deactivated. Here, 1, 2, and 3 are no longer active and have turned from red to blue. They correspond to the part of thought that has exited your attention. These have been replaced by neurons 8, 9, and 10, which are now active and shown in red. These three correspond to new concepts that have been added to your attentional window. The set of active neurons wasn't completely replaced, it was partially updated. This is because persistent activity of each neuron only lasts so long, and gradually the overall distribution of active neurons changed. Well, I'm arguing here that there's a direct correspondence between the gradual changes in neural activity, gradual changes in the stream of thought, and gradual changes in the subjective experience of consciousness. Namely, all three are updated iteratively. This makes it so that each state overlaps and blends with the ones that came before it, creating a continuous quality that gives experience its form and feeling. So contemporary models of how the mind works treat attention as a bucket that can be filled up and then emptied. As someone tells you their phone number, your attention fills. But if you're distracted or interrupted, the bucket is emptied and you start to fill it with something else. Once the bucket is full, it can't hold anymore, so it must be dumped completely before it can be filled again. And all existing models see the mind in this way. But what if the bucket doesn't have to be emptied completely? The present model sees attention as a bucket that is filled and emptied at the same time. So unlike in a pipe, the water inside the bucket gets a chance to mix. Here you can see the focus of attention attending to 4 items or mental representations at a time. The contents of attention search for the closest or most appropriate association as a newly selected update. This update is added to attention, but as you can see, as it's added, it displaces an item from attention into short-term memory. So the focus of attention is the bucket that's being filled and emptied at the same time. It's updated gradually, and thus successive states overlap with respect to their contents. After I explain this cycle in detail, we'll discuss how the next update is searched for and selected. The high-level conclusion is that the neurons underlying the contents of working memory spread their activation energy all over the brain, and thus work together to find the most closely probabilistically related association. This item then is used as the next update, and then of course, the search process is repeated in a continuous cycle. Next, let's quickly review some of the most popular models of working memory. So with any agent, be it an animal or a computer, you have input, processing, and output. You can also refer to that as perceptions, decisions, and actions. The input is received by the sensory organs, it's processed by the brain, and the behavior is enacted by the muscles. And then, of course, the performance of the behavior has an effect on the environment, which then affects the perception of that environment. So it creates a closed loop. Now, it really helps if you can remember how you perceived, what you processed, and how you acted, not just in the last cycle, but in several cycles before that. And this is short-term memory or working memory. Now, some cognitive architectures see it like this, where after you sense, you perceive, you perform a knowledge search, you plan, and then you decide before you act. And I think you can find a place for things like impressions, beliefs, and desires. But now let's delve into some of the more formal models. Here with the Atkinson-Shiffrin model, you can see information coming from the environment on the left, passing through sensory memory, which is mostly unconscious, moving into short-term memory, and remaining there if it's attended or rehearsed, and then if memorable, moving to long-term memory. Badley and Hitch's model shows that short-term memory is served by 2 subsystems, a visual spatial sketchpad, which lets you see and imagine things in your mind's eye, and an auditory rehearsal buffer, which acts as an echo in your head. That second buffer is shown there in the middle on the right, and is the reason why if I stop talking, you can pretty much hear the entire last second of what I said verbatim. Try it. The point is that these 2 subsystems help us maintain and manipulate information. For the last 15 years, I've had a special fondness for Bars and Gage's functional framework. It shows sensory information coming into the brain on the left. The information that is attended to enters working memory from where it can affect behavior there on the right. We also see the working memory storage interacting with the visual sketchpad and the auditory rehearsal from the previous model. For the most part, all of these models are complementary, and everything I will introduce will be too. In Barr's global workspace model, there are several systems that don't communicate with each other, at least at their lowest levels. This is indicated by the arrows on the side, such as attention, emotion, planning, sensory, and long-term memory. These all dump their outputs into a common workspace that can integrate this mixture of information. It's integrated, bound together, and then broadcast out to all the systems. In this model, consciousness arises there in the global workspace when information is unified and broadcast back to other processing centers. This is Cowan's embedded processes model. It shows working memory as an active subset of long-term memory, and now that concept has pretty much been accepted in the literature. We'll come back to this idea later, but as you can see, most of the models have a central executive, and that is basically a black box with a big question mark on it saying, we really don't understand how working memory is organized or controlled. But I'm going to argue that iterative updating is a key organizing element that performs much of the work that other theorists ascribe to this nebulous concept of a central executive. If you want to pause and study it, this figure recaps much of what we just went over. It shows how the three main memory stores can be decomposed into their component parts. This is one instantiation of the model I introduce here that we'll be working toward, but I consider it completely consistent with the other models we just discussed. It adds another dimension though and asks, well, what is happening to the items in working memory? How do we explain their dynamics? And seeing that half circle there on the left as a bucket that can be simultaneously emptied and filled gives us the perspective to see how. Now let's back up a little and start with some basics. Every time you have a thought about something, the corresponding memory for it in your brain becomes active. If I were to ask you to think about a cookie, a specific group of neurons or brain cells in your brain would start to fire as long as you think about the concept of a cookie. If I were to ask you to think about a cookie again, whether a minute later or a day later, many of those same brain cells and the same general pattern of activity would become active again. So there's a specific constellation of brain activity that corresponds to every concept that you know of. And you can see evidence of this using an fMRI scanner. In fact, if I handed you a cookie or merely showed you a picture of a cookie, it would reactivate much of that same brain pattern. When you have a thought about an object, like a cookie, a concept, like a mess, or a thing like Cookie Monster, there's a certain constellation of brain cell activity that corresponds to each of those concepts. But you never have just one concept active in your head. You would never have a thought about a cookie in complete isolation. Rather, you would co-activate a number of concepts that together create content. Usually a thought contains a subject, an object, and a verb. But the subjects of thought and the context they create do not all deactivate at once. Instead, some topics remain active as others are replaced with new topics. Thus, thought is partially updated on a continuous basis, making each instant a slight twist on what came just before. And modern models of working memory, as well as theories of consciousness, don't address this at all. So after the thought about Cookie Monster making a cookie mess, you might have thought about Cookie Monster cleaning up that mess of cookies. If so, 3 of the subjects have stayed the same over time, whereas 1 has changed. So in both states, you're thinking about cookies, a monster, and a mess. But in time 2, the representation for eating deactivated, and the representation for cleaning became active. This is one way to represent that, with red spheres standing for the activity of a mental representation and blue ones representing deactivation. This may help us to get to the core of how information is processed in the brain. So when a scenario arises, the brain pulls up existing representations from its repertoire that best describe or represent the issues at hand. The brain wants to have the most pertinent concepts available, and so it activates the item it predicts will be the most useful in the next moment. These updates help the animal respond accordingly at each step, ultimately helping it negotiate an event or scenario. Thus, the brain makes an iterative transition to another state with valid probabilistic properties. Valid in the sense that it should be helpful in contributing to the animal's adaptive behavior. Thus, working memory is simulating probable scenarios through iterative sequence generation. So here we see working memory on the left. Some of the items it holds currently will be retained, some will be subtracted, and some new items will be added. This will create a similar but different mix by the next state. Many of the major features of thought derived from introspection are addressed by this hypothetical explanation, such as how mental context is conserved from one thought to the next, how one thought is associated with the next, and how it logically or probabilistically implies the next. Brain scientists do not agree as to what exactly constitutes a thought, so thought is not a properly defined scientific term. But some sources estimate that humans have somewhere between 10,000 and 100,000 thoughts per day. This equates to around a thought per second. This model is the first to emphasize that many of these thoughts are blended conceptually and transform incrementally from one to the next. When you have a conversation with someone, when you perform a task at work, as you listen to a presentation, when you do virtually anything, you progress gradually through a series of related representational states. Imagine a scenario where the contents of thought B, C, D, and E were immediately replaced by F, G, H, and I. There would be no overlap in the items, and thus no iterative updating and no continuity. Here I'm arguing that it would not be possible for consciousness to exist in a system like this. Instead, this model points out that the experience of consciousness is made possible because the underlying brain activity does not change abruptly, but rather changes gradually over time. How about those gray rectangles that the active items lay within? Well, they represent a limited capacity store that cognitive neuroscientists refer to as working memory. So let's define working memory. It's a noun, and it's the components of the mind that temporarily hold a limited amount of information in a heightened state of availability for use in ongoing information processing. Traditionally, working memory holds items of information. These can include objects, shapes, colors, locations, movement patterns, symbols, rules, concepts, numbers, and words. When we imagine a scenario, we notice it transform into a related but distinctly different scenario. These two scenarios are related because our brain is capable of updating some working memory items without interrupting other items. A given line of thought does not change all at once, but rather makes additive transitions that are grounded by the content that remains unchanged. The subset of neurons that continue to exhibit persistent activity over the course of these incremental changes should be expected to embody the persisting subject of mental analysis. Stated differently, neurons with the longest lasting activation likely correspond to the underlying topic of thought that remains as other contextual features come and go. This allows potentially related representations to accumulate and co-activate despite delays between their initial appearances, ensuring that relevant processing products are temporarily sustained in working memory until a full suite of contextually related items are compiled so that they can be used in aggregate to inform behavior. When the items that are sustained are task relevant, working memory should be capable of incremental advancement toward a solution or goal state. Every waking instant, we're deciding what to add to the bucket, what to drain from the bucket, and what to keep inside the bucket, although of course most of this is decided unconsciously. So you might have noticed that working memory has a capacity limit. Let me explain quickly why here I depict it as holding 4 items at a time. To do so, we have to go back to George Miller, a psychologist who in the 1950s designed experiments to determine people's working memory capacity. He found that most people could hold around 7 numbers, letters, or objects simultaneously. For instance, try to remember this number, 4250709. If you had no trouble, then that means your working memory capacity was 7 for that trial. As you can see in this figure, 100% of people can hold at least 5 items in mind. 70% can hold 7, and only about 15% can hold 9. So George Miller figured that the working memory capacity for humans is 7 plus or minus 2. One of the reasons why phone numbers are 7 digits and license plates are around 7 characters is because of this 7-item capacity. For practical purposes, we can remember about 7 items, but for technical reasons, this number is closer to 4. Working memory researcher Nelson Cowan performed and analyzed many experiments that suggest that this number should be thought of as 4, and that is why I use 4 items in many of my figures here. Essentially, there are around 4 to 7 things that we can think of at once, regardless of whether these are visual objects in an array or words in a list. These figures could just as easily show the working memory capacity as 3 items, 7 items, or 9 items. Of course, you can imagine it in any way you like. So when I was first introduced to the concept of working memory, I started to wonder if even our thoughts are composed of 4 to 7 items at a time. I figured they must be. But does this give us a different perspective on the mathematical structure of how items behave as they stream in and out of thought? I think it does. So let's say that here in time 1, we have a snapshot of a thought frozen in time. Right now, memories for representations B, C, D, and E are active. A was active a moment ago, but is no longer active. F will become the next addition to working memory. When F is added, it does not replace all the other items. It only replaces one of them. In time 2, B was replaced, so C, D, and E remain. This means that C, D, and E persist in working memory and form an associative bridge between time 1 and time 2. I'm going to argue that this commonality between states links one mental moment with the next, allowing psychological progress, chains of reasoning, and creates the fabric of consciousness. So here we see this pattern playing out over 3 time periods. This process happens many times per second in a cycle and constructs the stream of thought. On the right is the full caption for figure 4 if you want to pause and read it. But next, let's talk about an exception to this diagram. Items of thought are not always going to exit in the same order that they entered. You can see that in time period 3, D was displaced from working memory and C was retained. In other words, out of alphabetical order. Thus, what deactivates is not necessarily what entered first. So the system is not what is known in computer science as first in, first out. It's much more flexible than that. So the item that is evicted is not the item that has been there the longest, but the item that is the least relevant. Now let's talk about how iterative updating can help us conceptualize a story. Imagine that item B represents your psychological concept of cookies. C represents your friend Cameron, D represents shopping, and E represents a grocery store. With these representations active in your working memory, you may form a mental image of your friend Cameron shopping for cookies at a grocery store. This scenario may cause you to think about Cameron's preference for milk to drink with his cookies. Thus, your next thought may be about your friend shopping in the same store for milk. So now this is turned into a story. Some of the context, the place, person, and activity remain the same, even though other aspects of the context, i.e. the object being shopped for, changed. Now that we're talking about stories and experiences, you can see that wouldn't make much sense to have a first in, first out structure where the item that had been there the longest is the first to be evicted. That would impose severe limitations on thought. And of course, that's great for us because it means we can think about cookies for as long as we like. So we have a system where a subset of representations is conserved from one thought to the next. This pattern of change enables continuity by allowing the context to shift incrementally, and I believe that this contextual shift is a central hallmark of the thought process. So some exceptions to our main figures so far have included working memory can hold more than 4 items, working memory is not always updated in strict alphabetical order, and now working memory is not always updated by 25%. So let's talk about the rate of updating. In this example, only one item is added and only one item is subtracted from working memory at a time. This would be a 25% update. You get that by taking the one item update and dividing that by 4 items to get 25. Of course, when all 4 items are replaced by new ones at 100% updating, attention is shifted to an entirely different topic. This is when you totally stop a line of thought in its tracks and pick up with a whole new idea. So this whole time we've been discussing 25% updating between 2 states. This is when you have 4 items and 3 stay the same, but you can also have more or less, such as 50, 75, or 100% updating as pictured here. This happens when thought shifts to something else. So in the case of 25% updating, you may be concentrating on something like reading a book. With 50%, you may be having a conversation with a friend. With only 75%, perhaps you're free associating or having a daydream. This final diagram on the bottom right shows 100% updating and 0 continuity, where none of the mental representations have been conserved. Here you've completely changed focus. Maybe you were cleaning something and then your phone rang. So it's not always the case that the majority of representations are conserved from one thought to the next. When they become a lower priority, all items in the focus of attention can be displaced at the same time. This readily happens when we're exposed to a new, salient, perhaps emotionally laden stimulus. Whenever a person loses their train of thought and forgets what they were just thinking, working memory in the focus of attention, though not in the short-term store, is interrupted. It jumps, reallocating attentional resources and reorienting to the new stimulus configuration and its accompanying set of features. Such a jump would constitute a disruption of or fluctuation in mental continuity. This figure features 7 instead of 4 items at a time. It also shows updating carried out over 4 time periods rather than just 2, and it compares a mind that is updating most of its content each cycle, there at the top, with a mind that's conserving most of its content each cycle, which you can see on the bottom. The figure covers a wider breadth of information and proceeds at a faster rate, but may be associated with an attention deficit, distractibility, and superficial associations. The bottom diagram is probably more conducive to concentrated attention, effortful or elaborative processing, and structured systematization of knowledge. This is because the search for the next state will be informed by a larger number of conserved parameters. Contrarily, in diagram 1, more than half of the initial parameters are excluded after only one time interval because they could not be maintained, and thus the next search performed loses precision and specificity. For example, it should be more difficult to solve a mathematical word problem in one's head using the updating strategy depicted in diagram 1 relative to that in diagram 2, because too many of the problem's crucial elements would be forgotten, and thus would not be available to contribute spreading activity in the search for a solution. The first diagram illustrates how neural activity in small-brained animals largely models the present and adjusts this model with bits from the recent past. The second diagram illustrates how neural activity in large-brained mammals models the recent past and adjusts it with bits from the present. Another way an attention deficit could show up would be not with the rate of updating, but with the frequency of 100% updates. This figure compares 3 major shifts in updating to just one major shift. The diagram on the left shows attention switching rapidly, basically exhibiting 4 discrete thoughts. The diagram on the right just shows 2 thoughts, and this style of thinking would be less fragmented. As a cognitive strategy, the processing found in the second diagram is probably more conducive to staying on topic, comprehending complicated scenarios, and solving complex problems. Okay, so back to the topic of partial updating. This shifting pattern we've been discussing can be described by 2 terms, recursion and iteration. So let's define them. Recursion refers to recurrence or repetition. It's also the repeated application of a rule, definition, or procedure to successive results. In computer programming, the goal of iteration is to obtain successively closer approximations to the solution of a problem. Because a number of associated representations can be sustained continuously in working memory, each brain state is embedded recursively in the previous state, amounting to a process that can progress toward a complex result. This is an example of mathematical recursion, and in the formula, you can see how repeating a recursive process can perform work or progress toward an end result. This is an example of optical recursion. This is a product of fractal or geometric recursion. And recursion is actually very common in nature. So here we have recursion because in time 2, 3 of the elements from time 1 reoccur. Next, let's talk about recursion's sister algorithm, iteration. Iteration is defined as the repetition of a mathematical or computational procedure applied to the result of a previous application, typically as a means of obtaining successively closer approximations to the solution of a problem. This drawing shows different iterations of the cell phone over time. Every new product, every iPhone or PlayStation, is a new iteration of the previous version. Developers take the existing version of a product, they remove what didn't work well, and then they add new technology, insights from R&D, and consumer feedback to create the newest iteration. The thought process works this way as well. That's why I call the model the iterative updating model. Shown with pictograms, it would look like this. You can see how iterative updating can lead to highly elaborated states that are comprised of select subsets of previous states. This corresponds to simple thoughts building constructively on top of each other to form complex thoughts. This is a form of compounding. This compounding makes it possible for a starting state to generate a chain of intermediate states that makes logical progress toward a terminal goal state. Here are some of the important terms that we'll discuss in one table in case you want to pause and take a look. Let's tackle them. Iterative updating is a partial shift in the contents of working memory that occurs during the updating as some contents are added, others are removed, and yet others are repeated. Here in time 2, working memory was updated with F, B was removed, and C and D were retained within working memory. So this is iterative updating. The next term is instantaneous coactivity, which is the coactivity of mental representations or neurons in a single instant or state. In time 1, B, C, D, and E are all in instantaneous coactivity. In time 3, C, E, F, and G are in instantaneous coactivity. It's worth noting that B and G never demonstrate instantaneous coactivity. Okay, and here we're getting to the meat, state-spanning coactivity, which is sustained coactivity of representations or neurons that span consecutive brain states. C and E are the only items that show state-spanning coactivity from time 1 through time 3. I abbreviate state-spanning coactivity as SSC. So SSC is quantifiable. The quantity of SSC can be thought of as directly proportional to the number of sustained nodes and the average length of time of their activity. If you have a minute-long daydream about you and your friend doing things together at the mall, a number of concepts may come in and out, but those three concepts of you, your buddy, and the mall would remain in state-spanning coactivity. And we can assume that, for the most part, the neurons that underlie those three concepts will also remain together in state-spanning coactivity for the same duration. In this example from earlier, 4, 5, 6, and 7 remained in state-spanning coactivity from one moment to the next. Next, we have incremental change in state-spanning coactivity, which occurs when some nodes remain in SSC and others are deactivated and replaced by new nodes. This is abbreviated as ICSSC. So incremental change in state-spanning coactivity, which you can see here, referenced at the bottom of this image, is taken to be the underlying neural substrate of mental continuity. It ties successive thoughts together. A fundamental assumption made by this article is that the content of working memory can be said to be in SSC, and as working memory progresses over time, the content can be said to exhibit ICSSC. Now you can replace the term working memory in the sentence above with any of these words: attention, short-term memory, consciousness, or thought. So let's do that with the word consciousness. The contents of consciousness can be said to be in SSC, and as consciousness progresses over time, the content can be said to exhibit ICSSC. Incremental change in state-spanning coactivity makes it so each state is nested within the last state, similar to these Russian nesting dolls. Let's define continuity. It's the unbroken and consistent existence or operation of something over a period of time. The manner in which ICSSC permits information from the past to conjoin and assimilate with information from the present may provide the connective tissue for the continuous nature of consciousness. In doing so, it may also permit continuity, one of the central features of consciousness. Iteration taking place at the level of consciousness causes consecutive mental states to overlap and be not only interrelated, but also interdependent and autocorrelated. Words like unbroken, gradual, recursive, and evolutionary are good descriptors. Continuous partial updating makes each mental state a reframed version of the last. This reframing process results in an updated group of conditions modulating rather than replacing the conceptual blend created by the previous set of coactive items. By the way, my effort to insert transitional sentences between these slides is an attempt at creating continuity, and we could model the concepts as I discuss them using the same red and blue ball method. So I'm going to argue that ICSSC in active brain cells creates ICSSC in the stream of thought and ICSSC in the experience of consciousness. The content of thought transfigures incrementally from one configuration to another instead of changing all at once. The thematic and narrative quality created by this continuity during internally generated thought may be largely congruent with key facets of mental experience. In other words, ICSSC imbues consciousness with a narrative or thematic quality. In literary terms, the subset of items that remain interdigitated constitutes the through line, connecting theme or invisible thread that binds elements of a mental experience together. Let's look at a few common thought patterns and model them with the present schema. So this figure shows someone having a thought, followed by an unrelated thought, but then they return to the first thought as before. This might happen when someone revisits an earlier thought, such as when rehashing a plan of action, retracing a set of previous steps, or retelling a story. This shows one thought followed by a second, but then the first thought picks up where it left off and continues to iterate from there. This might happen when someone picks a thought back up and continues to think about the issues from the last point at which they were considered. This shows a single thought that is discontinued, but then picked up from the middle. You can see that attention shifted backwards to a point in the center of the original sequence. This might happen when someone decides to assume a previous intermediate step in a problem-solving sequence and solve the problem in a different way. This shows what multitasking would look like given the present framework, where two lines of thought alternate every third time step but never actually combine or overlap. This context switching could occur when someone is working on two separate tasks or problems simultaneously. Here we see iteration occurring, but the first three items of thought never change. They stay constant as other variables are altered. This process would strengthen the connection between these first three items and explore how they're associated within different contexts. So maybe those first three items are you, your friend, and the mall, and the other items describe what the two of you would be doing at the mall. This is a line of thought that by the end has returned to where it started. This is when ideation goes full circle. Here we see the newest addition to working memory F is unhelpful or not task relevant. In this case, it's inhibited. The same items that recruited it continue to spread activation energy without being able to reactivate it. Multiple rounds of iterative inhibition may be required before an appropriate item can be identified. This kind of situation might arise as one deliberates over different methods of completing the same task, e.g., I should fax this letter. No, I should email it. No, I think I'll text it instead. Thus, each time a potential coactivate is vetted for exclusion, the search tree is restricted further. In 1020 AD, Guido de Arezzo created staff notation, which revolutionized the way musical composition was represented on paper. It denoted what notes were played, how long they were played for, a half note or a quarter note, and how they were arranged relative to other notes played. This work introduces a form of notation for the contents of thoughts. Staff notation is a mathematical graph of pitch with respect to time. This cognitive notation is a graph of items and how they're updated over time. This figure relates to the learning process. You can see that the person iterates from the concepts at time 1 to the set of concepts at time 10. Maybe they were wondering what cat food is best for their new kitten, and after thinking about it for a while and considering consulting the web, decided that they should ask their friend who's a veterinarian. Well, the next time they have this thought, instead of having to iterate through multiple different ideas, they can just go straight to their conclusion about asking their friend. And you can see there at the bottom, at time 98 and time 99. But let's talk in more detail about how the learning process might help us go straight from premise to conclusion. The contents of working memory, as well as the associations linking them, are saved to long-term memory, impacting future searches and ultimately permitting semantic knowledge. In other words, after time 1, the connections between B, C, D, and E will be a bit stronger, because as we know, neurons that fire together wire together. So that experience will be recallable. Because these sets of representations are recorded in memory, this process lays down tracks in the existing network, improving its predictive aptitude and future behavior. In other words, the thought process sets railroad tracks for the train of thought to travel down later. So if the connection between these concepts are burned in from being active together, and the connections between these are also, you can see that now B will be indirectly connected to F, and C, D, and E act as a linchpin between them. These are points of articulation that can be used in the future to guide the thinking process from B to F. And they link together chains of reasoning, ideas, and predictions. We could even think of them as channels or riverbeds for the stream of thought to be directed through. Taking this a step further, you can see how the contents of time 1, B, C, D, and E, could come to recruit the contents of time 3, C, E, F, and G, without having to iterate through C, D, E, and F first. And this allows us, the second time we consider some problem, to go from the premise straight to the conclusion. And that is what was going on in this slide here. To drive this home, let's make some more analogies. The first analogy is simple. It involves a tank and its treads. Individual treads are continually placed on the ground temporarily, and the treads that have sat on the ground for the longest are withdrawn in series. The total set of treads touching the ground in 1 second partially overlaps with the total set in the next second. The reallocation of information processing resources in the brain is similar. The set of active mental representations cycle in an analogous, although more flexible and stochastic manner. It could be visualized like this. You can see that each state overlaps with the previous state. I also see this organization as similar to the DNA molecule. It's like a linear polymer constructed from subunits. The subunits carry meaningful information and forge larger constructs. For DNA, those products are genes. For our model, they're actions. Again, your life record of iterative updating is like a blueprint containing instructions for formulating your behavior. And working memory runs down this serial sequence in the same way the zipper-like ribosome runs down the DNA molecule. Also, understanding DNA structure gives fundamental insight into how it operates, and I think it's the same with the model here. Allow me to introduce a third analogy. When you watch fireworks, a large constellation of points appears, disappears, and then is replaced by a new constellation of points. But now, imagine that it took 20 seconds for a firework to fade away. They would remain suspended in the sky. Their activity would overlap and would be much more dynamic and interesting to watch. Well, this is what happens with activity in the brain. Much of our brain's activity is lasting. In case you missed it, in this analogy, each item of working memory is like a firework. Please direct your attention to the pattern of activity within this woman's head. The pattern shown by the yellow dots has a distinct shape. It looks a little like a spiral galaxy. Now imagine some of these points disappearing and new points being added. For instance, imagine that point at the top right fading away and a new point becoming active near the middle. Over time, the overall shape would gradually morph into something else. The shorter the time difference between the two states, whether in seconds or milliseconds, the more similar in composition the two states will be. So looking at the activity in her brain, imagine what that activity pattern would look like 1 millisecond later. Not much different, right? But now imagine a full second later. After say 10 seconds, the pattern may be unrecognizable. When you have activity that fades slowly rather than disappearing abruptly, you have gradual, incremental change. A few more analogies may help clarify the nature of iterative updating. When it demonstrates continuity, we should expect the attentional spotlight to move slowly by degrees rather than abruptly. This makes it so that the components within the spotlight vary smoothly as it pans. It's like the carousel function used in computer graphical interfaces, where a collection of visible objects is updated as individual elements of the collection rotate into and out of view. It's also similar to the morphing technique used in computer animation, where an image is transformed fluidly into another by maintaining certain features but changing others in small, gradual steps. Corresponding points on the before and after images are usually anchored and then incrementally transfigured from one to the other in a process called crossfading. It's also like the changes taking place within the set of interlocking teeth of two gears. As the gears turn and a new tooth is added to this set, a different tooth is subtracted, yet the other teeth will remain interdigitated. It's also like the recursive effect you get when you point a video camera at a monitor displaying its own output. The next state of the system depends on the previous state's output, and a large degree of information is preserved between states. In both cases, you get self-referential circularity. Next, let's talk about the brain mechanisms responsible for this persistent activity. Experimental results over decades have indicated that the pattern of brain activity in any one instant does not disappear all at once. It's phased out. So from this we know iterative updating in ICSSC must be more than theoretical concepts. This support comes from related neuroscientific work into the cellular basis of persistent activity. There are two main forms of persistent activity in the brain: sustained firing, which is electrical, and synaptic potentiation, which is chemical. There are other forms of persistent activity which are currently being studied, but they're not understood very well, so we'll mainly focus on these two. Brain cells communicate with one another by firing at each other, or in other words, sending action potentials to each other. Sustained firing happens when a brain cell generates action potentials at an elevated rate for several seconds at a time. Here you can see the normal default firing pattern of a neuron, and below it you can see the firing pattern of a neuron exhibiting sustained firing. The action potentials are much more frequent. This more active state accounts for why you can remember what you were just thinking 5 seconds ago, because the neurons involved then are still heavily active now. As we said, the second mechanism is synaptic potentiation. Synaptic potentiation occurs when a neuron has been firing actively but has now become quiet. However, specific chemical changes at the connection between neurons, the synapse, make it more likely than usual to fire again if activated. This is why you can remember what you were just thinking an hour ago, because even though those neurons are not still firing, they're potentiated synaptically. So it's commonly accepted in neuroscience that sustained firing creates the focus of attention, and synaptic potentiation creates the short-term memory store. Working memory is these two stores added together. Scientists have understood this for only a few decades now, and it's really fascinating because it links physiological processes to psychological ones. So see that rectangle on the left? It shows items of working memory passing from the focus of attention to short-term memory, STM, and then to long-term memory, LTM. It's worth pointing out that only the FOA can undergo 100% updating. Why? Remember we discussed that the focus of attention can be completely updated when attention shifts to a new topic? Well, this kind of abrupt, non-iterative updating is not possible in the short-term store. This is due to the slower nature of turnover in synaptic potentiation. It takes hours for the chemical traces responsible for the short-term memory store to be completely erased. Because the number of active representations is much higher, and they subside much more slowly than in the FOA, the short-term store will continue to exhibit substantial iterative overlap, even during complete shifts in focal attention. Thus, the rate of updating from one period to the next is expected to remain relatively stable in the short-term store, whereas the rate of updating in the FOA is expected to fluctuate markedly under different processing requirements. However, both the focus of attention and the short-term store are updated iteratively. We know this because the sum total of synaptically potentiated neurons is equivalent to a pool that is constantly being added to as new neurons are potentiated and subtracted from as other neurons lose their time-limited potentiation. Thus, both the short-term store and the FOA demonstrate iterative functionality, albeit on different timescales. So, ICSSC, or iterative updating, occurs at two levels. One, the focus of attention, which is what you're thinking in the moment. It's a small, highly active subset of short-term memory made possible by sustained firing. It lasts from milliseconds to a few seconds. And two, short-term memory. These are representations previously in the focus of attention that are still activated above baseline, and they're made possible by short-term potentiation. This lasts for minutes to hours. Basically, you can recall the last slide because elements of it are in your focus of attention due to sustained firing. But you can remember the first few slides of this presentation because they're in your short-term store, made possible by synaptic potentiation. This figure shows two subproblems, and then those subproblems merging to reach a solution. So we start off with M, N, O, and P describing the problem. As you mull over the issue, you iterate and reach a subsolution O, P, Q, R. Q and R are then saved in the short-term store, and a related subproblem is introduced and iterated. Then part of the first subsolution is combined with a part of the second subsolution, and that is then iterated to generate a final solution. This might be you when you realize that before you can accomplish something, you have to complete two related steps. I think this is happening in our heads all the time. In other words, the focus of attention and the short-term store are constantly working together, passing concepts back and forth. So relating this back to our main recurring figure, those red working memory items in the gray rectangle correspond to concepts whose neurons are undergoing sustained firing. After this firing stops, they turn blue and remain synaptically potentiated for minutes to hours. Now let's relate these two working memory stores to inactive long-term memory. Let's zoom in on this model from Nelson Cowan. It shows that the focus of attention is just a highly active subset of short-term memory, and that the two together, working memory, is just an active subset of long-term memory. What does that mean? It means that working memory is merely activated long-term memory. Thus, any thought you can have is just a combination of a handful of active memories that already existed in your long-term memory. Thus, we piece our mental lives together from bits of things that we already know. So these letters or items, such as the concepts of a cookie, are just activated long-term memories. And this figure shows items flowing from the focus of attention and into the short-term store, and then into long-term memory. You might want to pause this slide to spend a minute with this table. It basically shows how sensory memory, held in sensory areas, has a large capacity but only lasts very briefly. The focus of attention holds 4 to 9 items and lasts up to a minute. The short-term store has a large capacity and can last hours, and long-term memory has a huge capacity and can last a lifetime. Basically, sustained firing keeps things at the forefront of attention, whereas synaptic potentiation keeps things in the back of your mind. So now that you understand the difference between the focus of attention and the short-term store, and you understand why each are updated iteratively, let's talk about how this helps us understand the shape of consciousness. To do so, we'll talk about this figure here. You can see from how it is labeled that the focus of attention is held concentrically within the short-term store. Thus, here are 2 states of working memory whose contents do not overlap. We can assume that these states are from separate thoughts. However, here we see 2 states whose contents overlap significantly. It's intended to represent a fractional transition in the thought process, such as 2 points in a line of reasoning. So you get it, right? Just to make sure, let me show you the equivalent examples underneath. So diagrams 1 and 2 show no Venn overlap between states from different periods. 3 and 4 show overlap in the short-term store only. 5 and 6 show the short-term store of one state overlapping with the FOA of the neighboring state. And 7 and 8 show the FOA of separate states overlapping, suggesting attentive continuity. Based on what we know about the timing of sustained firing and synaptic potentiation, it may be plausible that diagrams 1 and 2 roughly depict sampling of cortical activity hours apart. 3 and 4 depict sampling several minutes apart. 5 and 6 depict sampling every minute, and 7 depicts sampling every second. I believe this visual schema illustrates the structure of mental continuity. The shape you see is emblematic of the conveyor belt of consciousness. This is the experiential pipeline. I see this as the ego tunnel. So now that you understand the difference between the focus of attention and the short-term store, and you understand why each are updated iteratively, let's talk about how this helps us understand the shape of consciousness. It's now generally accepted in cognitive neuroscience that sustained firing allows us to keep mental representations in thought, allows the temporary maintenance of specific features, patterns, and goals. So a neuron may fire for 10 seconds, or it may fire for 60 seconds. Likewise, the neurons that encode the concept of cookies may fire for 10 seconds, or they may fire for 60 seconds, depending on what we're focused on. So here we're showing the concepts as a single blue line stretching across the horizontal plane. At time 1, B, C, D, and E are coactive together. Then in time 2, B is replaced by F. This is a different way of representing the pattern we were discussing before. When this pattern is repeated through time, ICSSC can be depicted graphically in the form of a gradually shifting stream-like distribution. This schematic of ICSSC reveals a repeating pattern. Remnants of the preceding state are consistently carried over to the next state. If this distributional plot were modeling neurons rather than representations, there might be millions of units per time period rather than 4. However, we can expect this fundamental recurring pattern would remain. This tells us that thought is composed of the startings and stoppings of individual elements that are staggered and overlapping. So the present model can be represented like this. Let's read the caption for this figure. Incoming information from motor and sensory cortices enters the focus of attention. The arrow on the far left indicates that as time passes, representations in the focus of attention decay toward a less active form of short-term memory, from which point they can 1. Re-enter the focus of attention, 2. Spread their instructions to sensory and motor cortex, or 3. Deactivate and return to inert long-term memory. This figure mentions sensory, motor, and association cortices, so let's talk about them next. Neurons in the pink areas here, which are known as association areas, have neurons capable of sustained firing. The colored areas, the red, yellow, purple, and blue, take a direct sensory input from a sensory organ like the eyes or ears, and do not exhibit as much sustained firing. Why don't they, you ask? Here on the left, you can see the optic nerve sending visual information directly to visual sensory cortex. On the right, you can see the cochlea of the ear sending information to auditory sensory cortex. It actually makes some sense why sensory areas do not exhibit sustained firing. If you looked at a scene and the neurons responsible for representing that scene stayed active for 10 seconds, then it would interfere with other incoming visual information. Persistent activity in sensory cortex would cause sights and sounds to blur. We don't want that, right? So neurons in these sensory areas quickly turn on and then off, so the new sensory input can replace the old, and you can stay up to date with what is happening in your environment from second to second. Imagine a television that had pixels that stayed active for 10 seconds each. It would be unwatchable. Rapidly switching on and off is a key property of LED panel pixels. The areas that show the most sustained firing include the prefrontal cortex, or PFC, there in the front, and the posterior parietal cortex there in the back. There, the pixels stay on for several seconds at a time. PFC neurons fire for sustained periods because they determine what aspects of the present environment should be maintained in working memory given the current scenario and its preceding circumstances. When confronted with a complex configuration of stimuli, the PFC selects the representations that it predicts should be temporarily maintained for their processing utility in the immediate future. On the other hand, primary visual cortex, there in the back, takes information from your eye's retina and registers the dots as if they were pixels. It processes this information and sends it downstream to later visual areas that connect these dots into lines. Higher areas connect lines into broader contours, and even higher areas use these contours to infer the presence of objects. So lower sensory areas see dots and lines, and higher sensory areas connect the dots to perceive broader objects. Association areas maintain representations of these objects and concepts, and of course, that is what we want to persist in mind. Objects and concepts, not dots and lines. This figure shows sustained firing activity occurring in 4 different forms of brain tissue: prefrontal, association, late sensory, and early sensory cortex. The finding in early sensory cortex doesn't last very long, and the firing in association cortex lasts several times longer. Here we can see that the neurons encoding representation A, shown in blue, stop firing, but those for B, C, D, and E, shown in red, are still firing simultaneously. This next figure shows a second graph, carrying this a little further into the future, from time 1 to time 2. Now B is no longer active, but F is. So again, even though concept B was dropped from state-spanning coactivity and F was added, C, D, and E are able to exhibit continuous coactivity from time 1 through time 2. The temporary persistence of C, D, and E ensures that they continue to transmit their effects on network weights as long as they remain active, biasing ongoing processing and affecting the interpretation of stimuli that occur during their episode of continual firing. This persistence ensures that the context from the recent past is taken into account during action selection. In other words, the longer the activity in these higher order neurons is sustained, the longer they remain engaged in hierarchy spanning, recurrent, and reentrant broadcasting throughout the cortex and subcortex. So we know that these 2 brain states share C, D, and E in common, and can be expected to share other commonalities, such as similar processing operations, similar search parameters, similar mental imagery, similar cognitive aspects, and similar experiential aspects. Thus, each state and the succession of states that make up consciousness share these commonalities, and I'm trying to convince you that this creates the essence and the feeling of consciousness. So let me say that again. The brain is a system that creates a succession of states with similar experiential aspects, meaning the conscious feeling you get from experiencing the content of time 2 is similar, or an updated version of, the feeling you would get from experiencing the content of time 1. I think this train or parade of similar experiential states is what fabricates subjective experience. If each state wasn't connected to the last in this way, we'd have no continuity, no traction for sentience, or any type of existential being. The highest areas, like the PFC, mix many different, highly processed sensory signals together. Again, for these areas, you want sustained firing, and you want a blur. If you didn't have this blurring overlap, you wouldn't have continuity, and each second would be disjointed from the second before it. It would be as if every moment you couldn't remember what you were just doing. So a sensory area processes incoming data from its sensory organ, but the association areas process information from multiple sensory areas they're surrounded by. They perform extra processing above and beyond just identifying sights and sounds. In fact, these areas mix sounds with sights, and that is why they're called multisensory or multimodal. Association areas are like the overlapping portions of a Venn diagram. As a brief aside, it should be clear now that ICSSC also functions like a Venn diagram. Of course, you can see that in this figure too. But here we're talking about the green and blue circles representing sensory areas and the association areas representing where they overlap. As you work up the hierarchy of association areas, you have areas like the PFC that have inputs from many different areas, including subcortical areas involved in emotions and motivation. These are like dense Venn diagrams. The PFC is parceled into several specialized regions, each of which is responsible for detecting, representing, and sustaining a different extraction of multimodal information. The PFC, along with a number of association areas, has been divided into increasingly smaller modules, each with unique receptive or projective fields and functional properties, including faculties such as short-term spatial memory, short-term semantic memory, response switching, error detection, reward anticipation, impulse suppression, and many others. In other words, these are all properties that can be preserved briefly in time and included in state-spanning coactivity. And the PFC and other high-level association areas are where the items of working memory that we've been discussing are held. So when you encounter a bird, the chirp is identified in auditory cortex, the feathers are identified in visual cortex, but the concept of a bird is identified in association cortex. Perception generally proceeds from the back of the brain, where incoming sensory perceptions are processed as they arrive, to the front, where they're recognized. Imagination, though, generally proceeds from the front of the brain to the back, as top-down processes control lower-order perceptual activity, like when I ask you to imagine a purple giraffe. But thought requires a loop between the two. Many neuroscientists think that consciousness arises from this oscillatory activity between high levels of abstraction and lower levels of abstraction. This is often called recurrent, resonant, or synchronized activity. I think this plays a role, but I think it's ICSSC that orchestrates this activity. This loop is augmented by state-spanning coactivity, which allows you to hold things in mind as you imagine what each iteration would look like and sound like, and as your language areas come up with the words to describe it. And when they do that, they do so iteratively. Humans have very large association areas, and this gives us an expansive working memory and a firm base in time. Most animals do not have this. They live their life in the moment from second to second without the ability to carry information with them for very long. Simple brain mammals, such as monotremes and marsupials, have very little association cortex. For example, the hedgehog has a cortex that is 90% sensory areas. It has little slivers of association cortex between its sensory areas, so we know that it cannot have much mental continuity. For comparison, our brain is the opposite of a hedgehog's. As you can see, our brain is mostly association cortex with little slivers of sensory cortex. There are many exceptions, but for the most part, animals that are more distantly related to us tend to have smaller association areas and less sustained firing. They have less state-spanning coactivity, but more incremental change in state-spanning coactivity. This equates to having smaller attention span. Thus, their iterative updating is more abrupt and less gradual than ours. For an animal like a fish, this means there are going to be fewer commonalities between one state of brain activity and the next. The fish brain is more like this. And the human brain is more like this, where persistent activity bridges longer spans. If you remember, when I talked about this earlier, I depicted it this way. Mammals encounter scenarios involving sets of stimuli that may remain relevant throughout the experience. A fish may not, but a squirrel would. In order to understand such a scenario, it's necessary to maintain mental representations of the pertinent contextual stimuli during the experience, and even afterward. With their big association cortices, mammalian brains are well equipped to do this. Mammalian working memory may harness iteration to allow potentially related representations to accumulate. This allows them to compile related sets of instructions that can be used in aggregate to form behavior. Non-mammals, and especially invertebrates, are not well equipped to do this. In simple creatures like the nematode or the fruit fly, association areas are minimal to non-existent. SSC is minuscule, and their entire working memory, if you could even call it that, is updated very rapidly. So they likely have very little mental continuity from second to second. With only 302 neurons, the nematode roundworm may have SSC and ICSSC on the level of brain cells, but not on the level of abstract concepts. They have no associative hierarchy to formulate high-order concepts, and this indicates to me that they would have very, very limited consciousness, if any. In mammals, however, SSC involves the coactivation of high-level representations from long-term memory within a single massively interconnected representational network, the cerebral cortex. This is one reason why I believe all mammals experience subjective consciousness. Compared to those of other mammals, human association areas contain more neurons, more intrinsic and extrinsic connections, and a higher capacity for sustained firing. These characteristics presumably permit us to retain more information for a longer time before it decays. This likely allows humans to better retain elements from recent thoughts, and allows the computational results of previous processes to more thoroughly inform subsequent ones. So we previously discussed one way SSC could be quantified. Employing the concept of a half-life is another. So we ask, how long does it take for half of the neurons currently engaged in sustained firing to stop firing? How long do you think it takes from this moment right here for half your neurons to drop out of SSC? If I had to guess, I'd say that rats likely have an average ICSSC half-life of around 1 to 2 seconds. Macaque monkeys twice this, and humans twice that. Does this sound right? Do you feel that half of your attention is replaced every 4 to 8 seconds? There are no scientists today that can give you a definitive answer. So like I said earlier, you're the expert. It's important to mention that even in a single individual, this half-life will vary depending on the task at hand, the level of arousal, the motivational state, brain oscillation factors, and brain regions assayed. So your half-life depends on what you happen to be doing at the time. The extent of iterative updating, or its half-life, may be a major facet of the general factor of intelligence. If it was properly standardized or operationally defined, it could be used as a psychometric marker. It may be a determinant of attention span, behavioral flexibility, working memory capacity, short-term memory capacity, reasoning ability, and general fluid intelligence. Individual differences in state-spanning coactivity may exist, and deficits may map onto clinical syndromes such as schizophrenia, intellectual disability, Alzheimer's, chronic stress, intoxication, prefrontal injury, and others. From here, let's go back and take an even closer look at the phenomenon of sustained firing. Patricia Goldman-Rakish was the first person to suggest that sustained firing is responsible for the information maintenance capabilities of the temporary storage buffers of working memory. Now, virtually everyone in the field agrees that sustained firing and synaptic potentiation are responsible for working memory. But how did she come to this conclusion? Along with Joaquin Fuster, she pioneered the use of single-unit recording of PFC neurons during temporary storage tasks. These tasks have been called delayed match-to-sample tasks. In the task, a monkey watched an experimenter place food under one of two identical objects. A shutter then lowered for a delay period so that the objects were not visible. After the delay, the shutter raised and the monkey was allowed one attempt to collect the food. After some training, the animals learned to choose the correct cup on the first attempt. This required holding the location of the food in memory over the delay period. Macaque monkeys are used to perform these delayed match-to-sample tasks. Many other types of mammals can perform well in this test, aside from primates including cats and dogs. The researchers concluded that because the animal can match to sample even after the original stimulus is no longer visible, they must be holding the stimulus in their working memory. They suspected that it is being held by sustained firing. Evidence for this came from the finding that an animal with a PFC lesion cannot complete the task. This influenced researchers to analyze activity in the PFC while animals were doing this task. Using implanted electrodes, experimenters were able to record from neurons in the PFC that fired throughout the delay period. The sustained activity subsided once the monkey's response was made, indicating that it was involved in representing the food location while it was out of sight. This landmark study first revealed the brain's mechanism for keeping important representations active without external input. If the monkey could successfully remember where the food was, they had neurons that fired throughout the delay period. If the monkey forgot, then it was because the sustained firing was cut short for some reason. It basically got distracted. This tells us that when you remember something that happened less than a minute ago, it's often largely due to the fact that the neurons involved in representing that thing are still firing away. In other words, you're aware of how the sentence started and can combine all the varied words that it contains into a single apprehension by the end of the sentence because sustained firing bridged the gap. So sustained firing creates an attentional context window. If the monkey's neurons didn't fire for long enough, they wouldn't remember where the food was. If my neurons didn't fire long enough, I might fail to make a mental connection, association, or insight. Or alternatively, I might just be letting go of an unnecessary detail so that I can focus on the most important ones. At the beginning of this lecture, I asked if the contents of thought correspond to items in working memory. Well, if this applies to one item, then it should apply to all the items in working memory. I was on the bus in 2005 reading about Fuster and Rakisha's work. It made me realize that everything I think about involves persistent activity taking place over time. I imagine that there must be many concepts, a stream of them, all perpetuated by the sustained firing of many individual neurons like those pictured above. And the fact that their activity is staggered and overlapping allows thought to be gradual, continuous, and iterative. Anyway, working memory, executive processing, and cognitive control are now widely thought to stem from the active maintenance of patterns of activity in the PFC, especially the dorsolateral PFC, where activates correspond to goal-relevant features and patterns. And this is totally consistent with the idea that higher regions of the cortex keep track of the big picture, while lower areas track the small, fast-changing details. But sometimes, even the big picture changes rapidly. Dopamine plays a role in this. As you might know, the dopamine system exerts complex actions on motor function, motivation, reward attention, learning, and delayed response. But it also plays a huge role in sustained firing. The ventral tegmental area pictured below is an emotional center that squirts dopamine into the cortex when we get excited or interested in something. Dopamine release directly increases sustained firing, strongly associating this system with SSC. Dopamine, and thereby sustained firing, increase in response to novel rewards and punishments, excitement, interest, fear, curiosity, incentive. Thus, these things structure the progression of thought by determining what remains in SSC. For the first 4 time periods here, the items are not retained very long. Then as dopamine is liberated in around time period 5, you can see that sustained firing kicks in and concepts are anchored upon, giving them more processing priority so that greater focus can be brought to bear on them. When dopamine fluctuates or a person attends a new stimulus, thinks of something else, or loses their train of thought, the rate of ICSSC can change. When we saw it earlier, it looked like this. Diving a little deeper into the neuroscience here will help us understand how the next iterative update is chosen. In other words, why F here is picked. This is important because it's going to determine which way thought is going to branch next. To do so, we'll take a look at cell assemblies. These are the neural building blocks that make up psychological items of thought. So this is a little disclaimer that tells you that I'm in full agreement with prevailing psychological and neuroscientific theories. The present model is consistent with connectionism and parallel distributed processing in that it conceptualizes cortical architecture as a plurality of densely interconnected networks composed of decentralized, semi-hierarchically organized pattern-recognizing nodes that have multiple inputs and outputs. There are likely 2 units or nodes that undergo iterative updating: assemblies and ensembles. Assemblies are small local groups of neurons, and ensembles are large groups of assemblies spread throughout the brain that code for mental representations. There are likely 2 units or nodes that undergo iterative updating: assemblies and ensembles. In this figure here, the assemblies are the small circles and the ensembles are the large ones. Donald Hebb invented the notion that a group of firing cells could represent a memory fragment in the mind for as long as the neurons remained in an active state. He called these groups of firing cells assemblies. Many neuroscientists today see the cortical architecture as an interconnected network composed of hierarchically organized, pattern-recognizing assemblies. In the present model, the engram for an item of the working memory is proposed to consist of a large set of such assemblies, likely located in multimodal association areas, which are thought to contain neurons that encode complex conjunctive patterns. Thus, in an active brain, an individual item of working memory would correspond to a subset of active neurons with strong interactions between them that are added to or subtracted from coactivity as a group. An assembly is a group of cells that work together to recognize a simple pattern. They've been termed microrepresentations, cognates, cognitive building blocks, subsymbolic pattern recognizers, coincidence detectors, or decentralized, semi-hierarchically organized nodes. A cortical mini-column is a vertical column through the cortical layers of the brain. They contain cells with similar response properties. These mini-columns form the cell basis of the activated long-term memory we were discussing earlier. So the assemblies probably correspond to mini-columns of cells in the cortex. These closely connected neural cell bodies in columns share the same basic structure and are thought to employ the same cortical algorithm. There are 200 million mini-columns in the human cortex. They are 30 to 40 micrometers in diameter, and they contain 80 to 120 neurons each. Each column has its own inputs and outputs, and each performs neural computation to determine if its inputs from other columns are sufficient to activate its outputs to the columns it connects to. We'll assume that to build a higher order mental representation, the cortex must combine a subset of the numerous fragmentary lower order units, assemblies or columns, at its disposal into an improvised composite. In this model, all high-order mental states are constrained in that they can only be built from combinations of pre-existing lower-order units. Because the neurons of such an assembly share highly similar receptive fields, the assembly responds to a particular preferred aspect of the environment and can be said to have a unique, although primitive, window on the world. So just like the neurons of which they're composed, assemblies compute a function that determines whether they should ignite or remain silent, whether the fragment of long-term memory that they encode should become active and contribute to working memory. If enough of their inputs fire at them, the cells of a column will fire as a whole, and in doing so, they send the following signal. Hey guys, the pattern I'm responsible for has been detected. Thus, the assemblies, like the neurons that compose them, recognize conjunctions and function as coincidence detectors or pattern recognition nodes. More intelligent animals, likely, have a larger number of assemblies in the cortex to select from, coactivate a larger number of assemblies simultaneously, and can prolong activation in these assemblies for extended periods. These assemblies form ensembles. Ensembles are groups of assemblies that code for higher order patterns that we're consciously aware of. They've been termed representations, invariant constructs, high order concepts, objects of attention, chunks, semantic pointers, abstractions, and so far we've been calling them items. Just to be clear, when a new ensemble is converged upon, it is the next iterative update. Ensembles are formed during learning. An ensemble is composed of cortical assemblies that have become highly connected in a Hebbian manner owing to approximately simultaneous activity in the past. The higher order representations they code for is distributed across this group of bonded neurons. It's unlikely that individual cells or even cell assemblies represent consciously perceptible constructs, but we'll refer to a coalition of assemblies that acts as an engram for a whole consciously perceptible construct as an ensemble. Here you see an ensemble depicted as a field of columns. Ensembles in association areas encode invariant, high-order representations, such as objects, people, places, rules, and concepts, as well as the propositions that define the nature of the relationship between these. Again, these spheres with the uppercase letters represent ensembles, and these lowercase letters are meant to represent cell assemblies. Here, ensembles B, C, D, and E are active. Here you can see that the assemblies corresponding to the ensembles for B, C, D, and E are active. Here we have an iterative update from ensembles B, C, D, and E to C, D, E, and F. And here we see the same iterative update on the level of assemblies. In the image on the right, B is no longer active and F is newly active. This is just like how in our story, Cameron stopped shopping in the store for cookies and started shopping for milk. So the brain transitioned from one state to a closely associated state. This transition was possible because some of these neural assemblies remained active over this time span, even though others did not. Next, we're going to work our way toward this figure. Here, the small spheres represent neural assemblies, and the large spheres that they make up are ensembles. As you can see, the active assemblies spread activity around the cortex, those red lines, resulting in the selection of the next ensemble, F. Here, the assemblies associated with ensembles B, C, D, and E unconsciously converge on the representation for F, and this is how I'm proposing mental associations work. Essentially, new representations join the representations that recruited them, are incorporated into the set of coactive parameters in working memory, and are used in subsequent searches. So the text above is a fancy way of saying that it may seem like we control our thinking. It may seem like we choose the next association that comes into mind, but that next association is not chosen by us or even by psychological logic. It's not determined by the concepts or their interactions. Rather, it's determined by probabilistic search carried out by the subsymbolic components of those concepts. And I call this multi-associative search. But let's unpack this a little further. What is it that's performing the work of working memory? This model predicts that it's actually the ensembles, the items of working memory themselves. The ensembles may perform a search function by sending electrical excitation to other ensembles. Associative networks spread activation energy from the active assemblies to inactive ensembles. The propagation of activation energy follows weighted links. The links, of course, are found in the dendrites, and the weights are found in the synapses. So for example, what is zebra here at the bottom connected to? Well, zebra is connected to panther, black, and white. So if you told this simple network to think of black, white, and panther, its closest association would be a zebra. Just imagine panther, black, and white becoming active and spreading their activation energy. It would spread all over this network, but the majority of spreading activation would converge on zebra. Now, your personal network inside your head is much, much larger, but works in much the same way. You can also see that if you excited rose, fire truck, and black, that the concept red would receive the most spreading activation and be activated. Thus, several alternate paths through these links can reach the same ensemble. This is called convergence. When enough of these links excite the same ensemble, it's activated. So here, B, C, D, and E spread their activation energy and it converges on F. One ensemble does not activate the next in linear sequence. Rather, many assemblies are co-activated together and pool their activation energy to determine which ensembles will be activated next in a nonlinear yet mechanistic manner. Thus, active subsymbolic representations work together to select symbolic representations, resulting in a self-perpetuating stream or train of thought. This is similar to the case where being exposed to the words coarse, current, wet, and bank might result in the involuntary search for and activation of the brain's representation for the word river. It's important to mention that both sustained firing and synaptic potentiation contribute to this spreading activation. So looking at this figure, what do you think would become active next if red, fire, truck, and siren were all active in the focus of attention? Probably firefighters, right? And then maybe siren would exit and water would enter next. So these are what I believe are the four determinants of the search for the next addition to thought. We'll cover each one briefly. Gradual additions to and subtractions from a pool of simultaneously co-activated ensembles occur as 1. Ensembles that continue to receive sufficient activation energy from the network are maintained. Here, C, D, and E are maintained. 2. Ensembles that receive sufficiently reduced activation energy or are inhibited are deactivated. Here, B is deactivated. 3. New ensembles which receive sufficient activation energy from the currently coactive assemblies are newly activated and added to SSC, and here F is added. I see these steps as similar to Darwin's steps in the process of natural selection. Those were variation, competition, adaptation, and selection. Mental continuity is an evolutionary process, and like natural selection, involves non-random retention and elimination of candidate structures, leading to incremental modifications to the population. Here, the assemblies that comprise ensembles B, C, D, and E are each individually associated with a very large number of ensembles, but as a group, they're most closely associated with ensemble F. This is analogous to the event where together the words radioactive, arthropod, nylon, and responsibility may together prompt the recollection of, can you guess? Spider-Man. And these four cues may have triggered the recall of Spider-Man despite the fact that by themselves, none of them are closely related to the character at all. It is the multi-associative aspect that creates the specificity. So the neural ensembles in your brain for radioactive, nylon, arthropod, and responsibility may have spread their action potentials around the brain and pushed the neurons that code for Spider-Man past their threshold, bringing your awareness of that friendly neighborhood wall crawler into mind. And now Spider-Man can be used as a search parameter along with the remaining parameters in the next search. So essentially, the present model depicts thought as the interaction between iterative updating and multi-associative search. And this figure shows that the next iterative update is influenced by many factors, including episodic, procedural, sensory, and semantic information. They all spread activation in the search for the next item or items. Consider the following Jeopardy trivia prompt. The name of a planet, an element, and a Roman god. I'll give you a moment to reflect. Does your brain converge on any one concept? You may have never seen this prompt before, but the clues may have contributed independently to unconscious neural convergence onto the ensemble in your brain representing the construct of Mercury. That's because you've seen instances where Mercury is either a planet, or an element, or a god. Ken Jennings and Brad Rutter, the two most successful Jeopardy players in the world, have been asked what reasoning process goes through their head when they answer a Jeopardy question. Both independently replied that they don't know, and that the answer seems to just instantaneously pop into their head. And I think this is why, and I think it underlies all thought. The brain employs a blind heuristic, summoning up the long-term memory fragments that are most probabilistically related to the currently active set of fragments. Thus, multi-associative search is an automatic and unconscious form of pattern completion. It could ultimately be responsible for not only the execution of automatic associations in an unconscious processing stream, but also sudden insight and even deliberate declarative associations. From this perspective, the contents of our next thought are chosen for us based on how the currently active assemblies interact with the existing nomological network. The current state will fall deterministically into the next most probable or stable state according to the prevailing neurophysiological conditions. This means that if you knew all the neuroscientific specifics of your brain, it would be possible to predict what your next thought is going to be before you think it. In other words, it may seem stochastic, but from a molecular view, it's deterministic. Essentially, this process uses working memory to fine-tune the brain's neurons and ensembles to get better at finding the most appropriate updates. It's a form of semantic or relational search that finds generalized similarities rather than exact matches for in-context learning. Now we're going to talk about how persistent activity allows delayed associations, or links between two things that present apart from each other in time. Let's say you hear a honk, and then a few seconds later you see a car, the same make and model as the one your friend owns. Because you can hold the honk in mind, it changes your perception, and instead of just seeing a red Toyota, you realize your friend is trying to get your attention. So two concepts may not have appeared in the environment at the same time, but if the brain can keep the signal representing the first concept active, it can meet up with the concept for the second. This means they can both feature in the spotlight of attention and be used together to build meaning. Sustained activity allows neurons that would otherwise never fire together to both fire and wire together. So persistent activity makes it so that Hebbian learning can occur without simultaneity. And this is how the brain determines cause and effect and captures long-range dependencies. Long-range dependencies meaning associative causal links between two things apart in time. When you heard the prompt, the name of a planet, an element, and a Roman god, sustained firing allowed those three concepts to meet up together in time, even though you encountered them at different points in time as you read the sentence. They were removed by thousands of milliseconds, but sustained firing helped them meet up together. This is true in the same way that B, C, D, and E all met up in time 1, but sometimes items fail to meet up. For instance, here B and G were never exposed to each other, and because of the limited capacity of working memory, an important association may have been missed entirely. The selection process for SSC is perhaps best exemplified by the ability to identify and maintain strategically important representations from a forthcoming scenario. A sentence, spoken or written, is a suitable example. A sentence will be comprehended if 1. The relevant representations are identified and enter into SSC. 2. All the necessary representations are sustained throughout the duration of the sentence. 3. The network has enough experience with this particular combination of representations to build the appropriate imagery, depicting them in the way they were intended. Now, most people have had the experience where either the wrong representations were anchored upon, or the right representations could not be maintained for long enough, and the sentence had to be repeated or reread. But most animals don't comprehend sentences. Instead, they parse and create understanding for events happening in their environment. The longer sustained firing and association cortex lasts, the better the animal will be at capturing information about causally linked stimuli that present apart in time. The higher SSC, the longer the delay can be. The same regularity may happen persistently in the environment, where a stimulus is followed several seconds later by another stimulus, concern, or opportunity. However, if the animal lacks sufficient working memory, this statistical regularity will not be captured by the neocortical system because the ensembles for them will never be exposed to each other within the focus of attention. Thus, iterative updating underlies the brain's ability to make internally derived associations between representations that never occur simultaneously in the environment. Few, if any, mammals have evolved a human-like capacity for sustained firing in PFC neurons, and thus the mental lives of most mammals likely involve associations made between temporally proximate stimuli and concepts. This may suggest that in most ecological niches, it's not helpful to create memories for relationships between stimuli that occurred in delayed succession, and instead, it's better to focus on analyzing stimuli that present in quick succession. Such animals are blind to relationships that are further apart in time. Their sustained firing does not last long enough to sew these together. For example, in insects, the only representations that fire together are those that present practically simultaneously in the environment, meaning that a stimulus from 1 second doesn't meet the stimulus from 3 seconds later. It's gone by that time. So a fly has a very hard time understanding cause and effect. Here at the top left, let's compare 1 and 2. In both cases, we have stimulus 3, or S3, but diagrams 1 and 2 show a different response to stimulus 3 depending on what came before it. The persistent activity of the first stimulus influenced the interpretation of S3, biasing the response accordingly. That is to say, the response to S3 is conditionally dependent on the stimulus that precedes it. For example, if someone calls you by your full name during a conversation, this could be a good thing or a bad thing, depending on what was said earlier. Diagrams 5 through 8 communicate that each item affects the interpretation of the items after it and uniquely biases the search for a response to them. At each time step, the preceding items provide a frame of reference by which subsequent items are interpreted. Consider a situation in which a person is writing with a pencil and the lead breaks. This may cause the long-term memory representation for writing, pencil, lead, and broken to become active in the FOA. This combination of coactive items, conditioned from years of writing with a pencil in school, might result in the automatic spreading of activation to the representation for sharpener. During another round of updating, the representation for writing may exit the FOA and be replaced by the pencil sharpener's location, such as desk drawer. In this way, sets of coactive items can prompt others in advancing sequences capable of producing not only predictions, but also adaptive behaviors. Especially when the items that are sustained are task relevant, this kind of iterative system should be capable of incremental advancement toward a goal. A rat could associate the sound of a knob turning and the opening of a door, but a dog could associate the sound of the garage door with the return of its owner. Apes are better in this capacity than dogs, and humans are better than apes. You may not be surprised to hear that adults are better than children. Sensory areas mature or myelinate early in development in mammals. Association areas, and especially the prefrontal cortex, doesn't fully mature until adulthood. What would you guess this means? Well, it means that infants and children create memories for relationships between stimuli that present in quick succession, whereas adults can see relationships between concepts out of succession. Because the frontal lobes of infants are underdeveloped, their brains probably exhibit far less continuity between states. Young children can trust the connections that their early sensory areas have made concerning the spatiotemporal associations between near simultaneous features because these events show high order and regularity. So this is what their brains trust them to analyze. This is why the sensory areas develop early in children. But when you're dealing with events that are removed from each other in time, it's probably difficult to know if one really caused or even affected the other. A young child's brain doesn't trust that they have enough knowledge to make the right inferences, and so it waits to allow the association areas to mature. Perhaps association areas are programmed genetically not to finish myelinating until early adulthood because it's a time-intensive process to form and test higher-order hypotheses about relationships between constructs that are more distributed through time. This suggests that at an early age, the first associations are between stimuli that are nearly simultaneous, but that these can create foundational knowledge upon which to base reliable inferences about associations between stimuli that are removed from each other by a delay in time. Sustained firing also allows features that never co-occur in the environment to be present together in mental imagery, such as when you're able to form a mental image of your buddy honking at you from across the street. And mental imagery is our next topic. Internally generated imagery, like that seen in the mind's eye, is created in sensory cortex. These areas use the contents of working memory as top-down instructions to build cortical imagery, aka topographic maps. Just like when Homer imagines a donut, he can see it in his head, sprinkles, pink frosting, and all. You can too. Try it. That imagery is held in your primary visual cortex, shown there on the right in blue. People that have brain damage to that area can't see things in their mind's eye. The visual area's brain tissue itself is organized like a map with a one-to-one mapping of the eye's visual field. That is why it's called retinotopic. Fascinatingly, this makes it possible to see letters in the activity among cortical columns in visual cortex. At the top is a picture of a pattern shown to a monkey. On the bottom is a stained portion of the monkey's brain tissue from its early visual cortex after being exposed to the picture. You can see the retinotopic map and the one-to-one correspondence between the image being viewed and the actual cortical tissue. This tissue comprises the bottom layer in the picture here. Its neurons project to higher layers that contain neurons that code for more abstract conjunctions or features. You can see it's going from lower levels of abstraction to higher levels. There are dozens of these layers in the visual system alone. The cortical hierarchy from sensory to association cortex arises because simple patterns converge upon second-order patterns, which in turn converge upon third-order patterns, and so on. This amounts to a hierarchy of increasingly complex representations stretching from sub-symbolic assemblies in sensory areas to analogically symbolic ensembles in association areas. Many pathways in the brain, such as the ventral visual pathway, appear to use a structurally descriptive architecture with compositional syntax, in which neurons or neural populations that encode low-level, non-accidental features are allowed to converge onto those that encode more abstract, higher-order, generic template-like features. This figure shows how these nonlinear transformations can accomplish hierarchical pattern recognition and completion. If you want to pause it and check it out. Many findings show that remembering or imagining an object largely activates the same neural networks that are involved in perceiving it in the environment. This has shown that in the brain, imagining something and actually seeing it are very similar. Most neuroscientists today assume that when we visualize and imagine, we construct and manipulate maps in early perceptual networks. The available population of assemblies and sensory cortex serve as an active canvas for either the environment via feed-forward connections or expectation and imagination via feedback connections to paint on. Thus, visual cortex takes the atoms from working memory and uses them to draw a composite sketch of whatever it is you're thinking of. So here we have items B, C, D, and E active in working memory. They're spreading activation energy all around the brain, and this is influencing the image that's being created in early visual cortex. The reciprocating crosstalk between sensory and association cortex may create progressive sequences of related thoughts, specifically because the maps generated by lower order sensory areas are guided by the enduring representations that are held active in association areas. Because they're drawing from a register with sustained contents, sequential images formed in sensory areas have similar subject matter and can thus be expected to be symbolically or semiotically related to one another. It's probable that the higher the SSC, the more related two sequential sensory images can be on average. Thus, we can expect iterative activity in association cortex induces early sensory cortices to produce sequences of interrelated mental images that build upon and buttress one another to form inductive predictions. This may produce sequences of symbolically related images, specifically because the enduring items sustained in association areas coordinate the construction of consecutive topographic maps. I call this progressive imagery modification. Progressive imagery modification depicts hypothetical events, explores causal associations, models relationships, and systemizes scenarios. So I believe that the same process that I termed progressive imagery modification not only happens in the visual spatial sketchpad as we've been discussing, but also happens with things that we hear in our mind's ear as well, otherwise known as the phonological loop. I think this allows the language areas of the brain to build speech iteratively and is responsible for the internal monologue or voice we hear in our heads. This process could similarly drive the progression of complex behavior in that the motor relevant representations that pass in and out of SSC impose iterative constraints on motor commands, and thereby regulate the animal's preparatory set, action sequencing, and planning behavior. This frames the brain as a system of numerous interacting modules that are each generating a mapping that is their most internally consistent composite interpretation of the other modules' mappings. Because the multimodal association areas have neurons that fire for sustained periods, they are better positioned to direct this activity through time. The rapid, rhythmic oscillations of information between sensory and association areas allow them to learn from each other and integrate their knowledge like two people in a conversation. The fact that they have fundamentally different perspectives makes the conversation dynamic and informative for both of them due to the lack of redundancy. The crosstalk is similar to that between two specialists in related areas, interrogating each other about the nature of their common interests. One of these specialists speaks figuratively and keeps a list of previous topics on hand. The other is a literalist and approaches each turn in the conversation with an unbiased, almost amnestic approach. So now let's talk about some more analogies. We started with the analogy involving the bucket. Then we discussed a tank tread analogy and a firework analogy. For a while, I imagined the cycle of thought being like Tarzan swinging from vine to vine under the jungle canopy. I imagined each vine corresponding to a new concept. As he swung like a brachiating ape, or like Spider-Man, he would be bringing new concept into thought with each swing. Some of the time he would hold two vines at once, and this would represent a transition between thoughts. But then it hit me that Tarzan doesn't have enough arms. Only holding two concepts at a time isn't enough to create real context. So then I started to imagine an 8-armed octopus hanging from the vines. The octopus travels through the jungle holding many vines at once, gradually repositioning. I liked this analogy much more. So the dynamics discussed here are captured by analogy involving an octopus grabbing and releasing footholds as it pulls itself from place to place. Octopuses really do this. It's an activity known as seafloor walking. The thought process involves co-activation of several representations at a time, which are the multiple footholds held by the octopus, deactivation of previously active representations, which are the release of those footholds, the activation of new representations, the placement of an arm on a new foothold. And remember, each arm has suction cups on it, and those suction cups make contact with the sandy ground. Thus, each arm is comparable to an ensemble, the suction cups are comparable to assemblies, and the sand underneath the arm is comparable to neurons. The octopus has a limited number of arms, so it must release footholds to free up arms to grab new footholds. Similarly, our working memory has a limited capacity and is constantly forced to reallocate its bioelectrical and hemodynamic resources. Coincidentally, the number of representational items that can be held in working memory, 7 plus or minus 2 by some estimates, neatly coincides with the number of arms an octopus has. So this way of walking exhibits ICSSC. And this analogy may be valuable because it depicts a system that even a child can understand, where specific representations are conserved through time as others are actively repositioned. So if we could create an electronic system that functions this way, could we create human-like artificial intelligence? What do you think? I'm only going to cover this subject very briefly, and I hope to do so in more depth in another video, but you can check aithought.com for much more right now. Why would it be important to understand how consciousness arises from the lump of pink matter in our heads? Scientists have pointed out many reasons, but I think it will inform the creation of conscious machines. A machine that is smarter than any person can build even smarter machines, and thus, through recursive self-improvement, accomplish things beyond our wildest imaginations. As Nick Bostrom said, the first ultra-intelligent machine is the last invention that man need ever make. So modern computing hardware holds information in short-term memory and long-term memory, and information is passed between them, just like in the brain. Moreover, information in CPU registers, CPU cache, and in RAM are coactive and exhibit instantaneous coactivity, just like in the brain. The contents of computer memory overlap through time. Between one clock cycle and the next, you may have a large number of memory items that show sustained activity in each of these memory stores. This technically means that computers exhibit a form of state-spanning coactivity, but I don't consider them to have iterative updating or any kind of working memory, because the memories used by the CPU are very much isolated from one another. In other words, the memories held in RAM are coactive but not co-spreading, meaning they don't do this. The red ensembles here on the left are coactive and co-spreading. By this I mean that they pool their activation energy to perform a search. This just doesn't happen in computer memory. Computer states are isolated and time-locked. They do not exhibit true ICSSC, and thus there's no mental continuity in such a system. Even in contemporary artificial neural networks, such as recurrent networks or transformers, ICSSC and multi-associative search are not harnessed for information processing. Computers don't do this. The model described here could be used to inform the construction of a multi-modular neural network AI architecture that harnesses ICSSC for use in pattern recognition, analytics, prediction, adaptive control, decision-making, and response to query. The system would use active information in working memory to search for related or entailed information. Each state would be a search for the next state. The system would not suspend its activity every time it finishes a task, rather it would exhibit continuous endogenous processing. Rather than only being active during training and response, it would continually be in a state of thought, which would perpetually fine-tune its weights. Nodes in multimodal areas should be capable of persistent activity, simulating the sustained firing of pyramidal cortical neurons. When the persistent activity abates, these nodes should have a capacity to simulate synaptic potentiation. This would enable the nodes to maintain pertinent, high-level patterns in a simulated FOA, and then a short-term store, over elapsing time. Prioritized features sustained in association networks could be used to guide the construction of topographic maps in sensory, auditory, motor, and language networks. So this was an early schematic, but this next one is better. The program will be composed of several highly interconnected multi-layer neural networks of pattern-recognizing nodes organized into a hierarchical architecture similar to that of the mammalian neocortex. The multiple interfacing neural networks would be arranged biomimetically, i.e., connected and tuned to simulate sensory and association cortices. Like neural assemblies, the nodes would exhibit a continuous gradient from low-order nodes that code for sensory features and serve in feature extraction, to high-order nodes that are designed to capture and encode temporally or spatially extended relationships between such features. Networks at the bottom of the hierarchy, there on the left, take input of a single modality from the environment. Other networks take input from multiple neural networks below them in the hierarchy, making them multimodal. Spreading network activity would oscillate between the top and bottom of the hierarchy while allowing recurrent feedback between and within networks, creating a seriocognitive cycle. This figure features 24 networks, each with 19 nodes. An actual build would necessitate dozens of networks, each with millions of nodes. This provides more detail if you'd like to read it. Replicating ICSSC using deep learning algorithms could make it possible for large multimodal neural networks to recognize invariant patterns whose components are distributed across time. This capacity may then allow them to find higher-order structure in unlabeled data, integrate abstract knowledge, and perform logical inferences in uncertain environments. This figure compares the number of nodes that have remained active in a normal human, in a human with frontal lobe dysfunction, and in a hypothetical AI agent. The AI agent can maintain a larger number of nodes over a longer time span, ensuring that its perceptions and actions in T1 will be informed by a larger amount of recent information. If the sustained activity of higher order nodes was programmed to persist for extended intervals, an AI system could exhibit a superhuman capacity for continuity. This could amplify the ability of the network to make associations between causally linked but temporally distant representations, and allow its processing and actions to be informed by more temporally distant concerns. It could also allow the imagery that is created to be informed by a larger number of parameters and ensure that important features were not omitted simply because their activity could not be sustained due to biological limitations. To operate meaningfully and reduce its propensity for recognizing false patterns, such an ultra-intelligent system would require extensive training. And for the same reasons discussed earlier in relation to myelination in developing humans, I think that this superhuman ability for persistent activity should be introduced into the AI system slowly as it learns to make associations across time. In other words, the AI should start its life using the middle strategy and transition towards the bottom one as it gradually builds a worldview. Programming AI working memory stores to maintain relevant items for longer periods than their biological counterparts could increase their ability to make valid associative connections between causally linked events separated by long delays in time. In other words, an extended attention span could increase the recognition of long-term dependencies, resulting in the perception of higher-order patterns and abstractions that are imperceptible to humans. Prolonging persistent activity in this way could also allow each search to be more specific and informed. This is because searches would be apprised by a larger number of specifications that stretch further back in time. It would also ensure that the system is less likely to allow crucial intermediate solutions to decay from working memory, i.e. a cache miss, before they're needed to form high-order compound inferences. The thoughts of such a system would be lengthy, highly focused, and tightly woven. This shows how the AI's attentional window could be expanded to increase its capabilities. Here in the top left, you see a human with a working memory capacity deficit. To the right of it, an attentional deficit. The bottom left is a normal human, and the bottom right shows an artificial superintelligence. Next, we address how do conscious and unconscious processes relate. Consciousness may actually consist of unconscious processes exhibiting ICSSC, arising when automatic impulses implement the same suite of representations for a prolonged period. Thus, just one of these cycles doesn't produce any consciousness, but multiple cycles do. In other words, the selection and addition of a new item to working memory is not conscious. It's not declarative or deliberate. The level at which thought articulates is unconscious. But as this process cascades through time, it gives rise to consciousness. When a series of unconscious processes are linked together, guided by a set of representations held in persistent activity, they become conscious. In cognitive psychology, dual process theory suggests that implicit and explicit processes use two fundamentally different cognitive processing architectures, System 1 and System 2. System 1 is implicit, automatic, and unconscious. It operates quickly, effortlessly, and has a large capacity. System 2 is explicit, controlled, and conscious. It operates with effort and has a smaller capacity. These two systems are thought to be subserved by distinct neural substrates. I believe they share the same general neuroanatomical foundation, and that System 2 is actually System 1 exhibiting ICSSC. That is, what is referred to as System 2 may simply be the processing architecture of System 1, top-down to bottom-up reciprocations within the thalamocortical hierarchy, implementing the same suite of representations for a prolonged period. Again, System 1 is making automatic, intuitive flash judgments. However, because of SSC, these rapid associations are able to support each other in a progressive and additive manner. Rather than arriving at a judgment about something based on a single impulse, System 2 may involve the sequential arrangement of several impulses that cooperatively lead to a higher order judgment. Iterative updating may allow previous states to set premises for subsequent states, allowing logical operations. System 2 cognition may be involved in a mental task whenever ensembles related to the task exhibit sustained firing and are utilized in progressive imagery modification, culminating in sensory imagery or motor output that could not be informed by any of the intermediate steps alone, or that is capable of solving a problem too difficult for any System 1 process itself. For example, early processes may provide premises or propositional stances that can be used algorithmically, e.g. syllogistically, to induce or justify a conclusion in subsequent processes. Perhaps reciprocating activity between SSC updating system and the imagery generation systems produces sequences of interrelated mental images that build upon and provide scaffolding for one another to form logical deductions and abductive expectations. Researchers in psychology suggest that System 2 processes are initiated by motivation, surprise, and curiosity. Of course, these are the same three factors involved in recruiting the mesocortical dopamine system necessary for the sustained firing responsible for ICSSC. Iterative updating may allow the implementation of learned algorithms, using one state to recruit the next until a final goal state is reached. Learned mental operations have algorithmic steps that must be executed in sequence to reach completion. Foraging, tying shoes, and performing long division all involve following an algorithm. Successive states of working memory may correspond to successive steps in the algorithm. Iterative updating may be instrumental in implementing learned algorithms because virtually every step of an algorithm refers to the preceding and subsequent steps in some way. A newly updated item would correspond to an action or mental operation needed in the next step. For example, multiplying two two-digit numbers may be a mental calculation that involves a series of System 1 impulses coordinated to implement a learned pattern of algorithmic steps. All learned mental operations probably have distinct, predefined algorithmic sequences of topological mappings that must be completed in sequence to achieve the solution. Each brain state would correspond to a different step in the algorithm, and because each was trained to do so, its activity would recruit the next step. When you get to this point here, how do you know what to do next? This registers the context and prompts it for you. Francis Crick and Christoph Koch have advocated that neuroscientists should concentrate on finding neural correlates of consciousness, defined as the minimal set of brain mechanisms and events sufficient for some specific experiential state. ICSSC, as described here, may be a strong candidate for a neural correlate of consciousness. The reasoning here suggests a consideration of consciousness as an elaborative process, where the longer a set of representations is maintained within SSC, the more conscious one becomes of that subset. ICSSC may be necessary to form higher order or transitive representations, i.e. a representation of a representation, and thus may be necessary for active self-awareness. In other words, self-consciousness may necessitate that common notions about the autobiographical self remain in SSC, where they help to direct the progression of images and impulses. Well, how about that elusive philosophical concept of qualia? Well, qualia may gain their experiential qualities when their features are maintained in SSC, volleyed between association and sensory areas, and used to uncover apposite memories and images. This process could be conceptualized as experiential or phenomenal continuity. But hopefully by now you can see how ICSSC and iterative updating give rise to continuity, and how this continuity could play a major role in clarifying the hard problem of consciousness. I think this is what experiential continuity looks like. I see this as the shape of consciousness, and I'm arguing that consciousness arises because of shared content between states of working memory. The present line of thinking may cause us to ask, could ICSSC be used to quantify the extent of consciousness in animals? Could its absence be a marker of coma or vegetative state? Is it necessary for human-level intelligence in machines? And what form of phenomenal experience or sentience could an entity possess if it exhibited no ICSSC? So now we move on to the conclusion. The model presented here is intended to inspire more detailed hypotheses that can be tested experimentally and against already existing experimental data. Further research should look for the distinct neural signature of ICSSC within the cerebral cortex. This search for the iterative signal should involve extensive time series analyses of simultaneous recordings on sub-millisecond timescales from small groups of neurons in many places in the brain. This figure shows recording of activity from several neurons. It looks like a mess until you know what to look for. The brackets at the bottom show how this mess can be parsed into individual items. In other words, existing recordings probably contain the signature of consciousness within them. This figure depicts working memory as being composed of a large number of functionally specialized stores intended to indicate that items may exist along a graded continuum of activation. I consider this model to be consistent with a large number of theoretical models in the scientific literature, including these. This model can also be integrated into a number of existing cognitive architectures, such as these. Here's a table with some of the terms introduced in this article. In his book, The River of Consciousness, Oliver Sacks asks, but how then do our frames, our momentary moments hold together? How, if there's only transience, do we achieve continuity? This article has argued that our momentary moments overlap in their set of active representations, and that this constant overlap assembles a seamless progression of states in which each state does not die off, but continues into the next state. After asking the question, Sacks quotes William James. Consciousness then does not appear to itself chopped up in bits. Such words as chain or train do not describe it fitly as it presents itself in the first instance. It's nothing jointed. It flows. A river or stream are the metaphors by which it's most naturally described. In talking of it hereafter, let us call it the stream of thought, of consciousness, or of subjective life. As the brain changes are continuous, so do all these consciousnesses melt into each other like dissolving views. Properly, they're but one protracted consciousness, one unbroken stream. The present model bears a resemblance to James' conception of a stream of consciousness. A stream is a distribution of points that slides through space and time. Figure 22 extends the activity schematized in this article's other figures over 13 points in time. This results in a depiction of brain activity, working memory, and thought that, shifting gradually, appears very much like a stream. This figure goes farther than the others we've seen thus far, incorporating a larger number of the present model's theoretical features. These include the number of items varies between 3 and 5. 2. The percentage of updating in the FOA varies between 25 and 100%. 3. The order of entry into the FOA does not determine the order of exit. 4. Items that exit the FOA briefly enter the short-term store, gray spheres, before deactivating completely, black spheres. And 5. Items that have exited the FOA are capable of re-entering the FOA. So this forms a more realistic abstraction than the more emblematic figures that have come before. I think this famous quote from Charles Sherrington is also helpful. Swiftly the head mass becomes an enchanted loom, where millions of flashing shuttles weave a dissolving pattern, always a meaningful pattern, though never an abiding one, a shifting harmony of subpatterns. So he's saying that consciousness is a dissolving pattern, made up of subpatterns that are constantly shifting. I like to think that Sherrington's dissolving pattern may directly correspond to the gradually transforming distribution of temporarily sustained representations undergoing ICSSC. So I like the idea of an enchanted loom. I think it helps illustrate iterative updating by showing how you can have a process that simultaneously exhibits both deterioration and accretion. I think that this underlies our ability to transition between closely related thoughts. And I think that it may constitute the physical fabric of consciousness. Whether a series of actions, words, or musical notes, each is delivered separately in its own discrete span of time. But our brain's capacity for iteration allows us to knit these temporally isolated stimuli together into performances, speeches, and melodies. This attribute permits mammals to weave together threads of isolated objective occurrences into a continuous tapestry of subjective experience. Thank you for your time, and thanks for listening. And again, you can read over the article at Physiology and Behavior, take a look at the 2023 article on arXiv, or visit aithought.com.